Good morning, everyone. I am Pallavi. Today I am going to explain 5th lab program Design Verilog HDL to implement decimal adder. Before getting into the program, first we will understand what is decimal adder. Decimal adder is also known as BCD. BCD stands for binary coded decimal. It is used to perform the addition of BCD numbers. In BCD, each digit is typically represented by a fixed number of bits, commonly 4 bits, making it a 4-bit binary code for each decimal digit. The minimum value of BCD is 0 and the maximum value is 4. Here is the simple example for BCD. We are adding A and B where A is equals to 7 and B is equals to 8. In binary, 7 is equals to 0, 1, 1, 1 and 8 is equals to 1, 0, 0, 0. The sum of both A and B, that is 7 and 8, is 15 in binary, that is 1, 1, 1. If value of y is greater than 9, then we should add 6 to it. As a result, we'll get 10101. This is the 4th bit decimal order program. Input A is to 0A and input A is to 0B. This declare 4-bit input A and B, assuming each input represents the decimal digit in BCD form. And the output 4 is to 0 sum, this declare 5-bit value. The output sum, which is expected to store the result of the addition. Assign sum is equals to A plus B performs the addition of A and B in module. And here is the output. We assign 6 for A, which is 0110, and 9 for B, which is 1001, and sum has 01111. Thank you.
Hello, I am Pallavi. Today I am going to discuss about the subject that is digital design and computer organization, in which I am going to discuss about the topic multiplexer. Before going to delve into the topic, it is essential for all of us to know about what is multiplexer. Here's the definition of the multiplexer. A multiplexer is a combinational circuit that accepts several input signals and forwards the selected input to the single output line based on control or select signals. And the basic operation of the multiplexer is a multiplexer uses select lines to choose which inputs to pass to the output. The number of the select lines is determined by the number of the inputs. Here, 2 is to 1 multiplexer accepts 2 data inputs and it consists of 1 select line. And the truth table of the 2 is to 1 multiplexer is given here. And 4 is to 1 multiplexer consists of 4 data inputs and it consists of the 2 select lines. And the truth table for the 4 is to 1 multiplexer is given here. 8 is to 1 multiplexer. 8 is to 1 multiplexer consists of 8 data inputs and 3 select lines. The advantages of the multiplexers are it reduces the hardware requirements by combining inputs and facilitates the efficient data transfer. And the application of the multiplexer is a data routing in processors, logic function implementation, communication system for data selection. Here today I am going to discuss about the 6th program of the DDCO, that is design a Verilog program to implement different types of multiplexers that are 2 is to 1, 4 is to 1 and 8 is to 1 multiplexers. Here 8 is to 1 multiplexer. Here I am going to in the module as mux, and here S is the select lines and D is the inputs and Y is the output. As we all know that a multiplexer accepts 2 or more inputs and it provides one output. In 8 is to 1 multiplexer, it accepts 8 inputs and provides one outputs, and it consists of 3 select lines. Here the output is Y and the register is named as Y, and here S represents the select line, and here from 0 to 7 the inputs are given. And then we are going to end the case and end the module. Next, moving on to the 4 is to 1 multiplexer. Here we are naming the multiplexer, this module as MUX again, and here S is the select line and D is the inputs and Y is the output. In 4 is to 1 multiplexer, there will be 4 inputs and 1 output and 2 select lines. Here the output is Y and the register is named as Y, and here S represents the select line, and here from 0 to 3 the inputs are given, and here we are going to end the case and end the module. Let's move on to the 2 is to 1 multiplexer. And here the module is again named as MUX, and S is the select line, and D is the input, and Y is the output. Here the inputs are provided two inputs, and it will provide one output, and the select line will be one. Here the output is Y, and the register is named as Y, and here S represents the select line, and 0 and 1 are the inputs given to it. Here we are going to end the case and end the module. And the corresponding output for the given bedrock code is given here. For 2 is to 1 multiplexer, the select line is 1 and the inputs are 0 and 1 and the output is 0, and the corresponding output for the this input is given here in microseconds. Here the for 4 is to 1 multiplexer, the select line is 1 1 and the input is 1100 and the output here is 1. So the corresponding output screen is given here and at microseconds. And here 8 is to 1 multiplexer, the select line is 111 and the input is 011011010. So the output is 0, and the output for this is given here. That's all about my today's explanation. Thank you so much.
Hello everyone, I am Pramata and I am here to explain the 7th lab program of the subject DDCO. First, let us go through the question. The question goes like, design Verilog program to implement demultiplexer. First, let us learn what is demultiplexer. A demultiplexer, also called as a DMUX, is a device that takes a single input line and routes it to one of the several digital output lines. It consists of two N outputs and has N selection line, which are used to select which output line to send the input. It is also called as data distributor. Moving forward, here we can see it is a 1:4 demultiplexer. I represents the input line. S1 and S0 are the selector lines, which can take the values 00, 01, 10, and 11. And Y0, Y1, Y2, and Y3 are the output lines. Now, moving forward, let us go through the program of the demultiplexer. Here, S and D are the inputs and Y represents the output. Input of 1:0 of yes represents the 2-bit selection line. Input D is a 1-bit data input. Output of 3:0 of Y shows the 4-bit showing output. Register of 3:0 Y is a register 4-bit to store registered value. Always at yes or D is a always block which executes when there is a change in yes or D signals. Now, getting inside the always block, Y of 3:0 is equal to 0 initializes all initial bits to 0. Case of yes is a switch statement based on the value of yes. If yes is 0, then it sets Y of 0 to the value of D. If yes is 1, then it sets Y of 1 to the value of D. If yes is 2, then Y of 2 to the value of D. Then if yes is 3, then it sets Y of 3 to the value of D. Moving forward, let's go through the output. If yes is 0, 0, then value of 0 will be set to the value of D and the other output lines will remain at 0. If yes is 0, 1, then the value of 0, 1 will be set to the value of D and the other output lines will remain 0. If yes is 1, 0, then value of 1 will be set to the value of D and the other output line will remain at 0. And if yes is 1, 1, then value of Y will be set to the value of D and the other output line will remain at 0. To summarize, the value of Y of 3:0 will reflect the value of D on the specific output lines determined by the value of yes. Thank you.
Good evening, everyone. My name is Nidhi Joshi, and I am here to talk about the topic flip-flop. To know what is flip-flop, the flip-flop is a circuit that maintains a state until directed by input to change the state. A basic flip-flop is constructed using 4 NAND gates or 4 NOR gates. Flip-flop is popularly known as basic digital memory circuit. We have 4 types of flip-flops: SR flip-flop, JK flip-flop, D flip-flop, and T flip-flop. To know what is SR flip-flop, SR flip-flop. In the flip-flop, with the help of present, and clear, when power is switched on, the state of circuit keeps on changing. That is uncertain. It may come to set of Q equals 1 or reset Q not equals to 0 state. In many applications, it is desired to have initial set or reset, the flip-flop that is initial state of a flip-flop that needs to be assigned. This thing is accomplished by the preset or the clear. We have the SR flip-flop diagram here where we have three inputs, S, CLK that is clock, and R, and two outputs, Q and Q naught. We have four NAND gates in the circuit diagram of SR flip-flop, and here we have the truth table of the SR flip-flop. We have four operations of SR flip-flop. The case 1 is when PR is equals to CLR is equals to 1. The asynchronous inputs are inactive and the flip-flop responds freely to S, R and CLK inputs in the normal way. The case 2 is where PR equals 0 and CLR equals 1. This is used when the Q is set to 0, that is output Q is set to 0. Case 3, PR equals 1 and CLR equals 0. This is used when Q dash is set to 1. We have the last case, that is case 4, when PR is equals to CLR is equals to 0. This is an invalid state. The next we have JK flip-flop. In JK flip-flops, the basic structure of the flip-flop consists of the clock, clear and the preset. We have the block diagram of JK flip-flop and JK flip-flop circuit diagram which has 4 NAND gates, and we have the truth table of JK flip-flop. As same as SR circuits, we have operations for JK circuits, that is case 1 where PR is equals to CLR is equals to 0. It is an invalid state. And the case 2, again PR is equals to 0 and CLR is equals to 1. The PR is activated, which means output in the queue is set to 1. Therefore, the flip is in this set state. Case 3, PR is equals to 1 and CR is equals to 0. The CLR is inactivated, which means the output in the Q dash is set to 1. The case 4 where PLR is equals to CLR is equals to 1. In this condition, the flip-flop works in its normal way, whereas the PR and the CLR gets activated. The next we have is D flip-flop. The D flip-flop consists of a single data input, a clock input and two outputs, Q and Q dash. We have the block diagram and the circuit consists of 4 NAND gates and a NOT gate, and this is the truth table. Again we have 4 cases for the D flip-flop. The case 1, PR is equals to CLR is equals to 0. This is the condition. This condition represents as invalid state where both PR and CLR inputs are inactive. Case 2, PR is equals to 0 and CLR is equals to 1. This state is the set state in which PR is inactive and CLR is active and the output Q is set to 1. Case 3, PR is equals to 1 and CLR is equals to 0. This state is a reset state in which PR is active and CLR is inactive, and the complementary output, that is Q dash, is set to 1. PR is equals to 1 and CLR is equals to 1. In this state, the flip-flop behaves as normal. Both PR and CLR inputs are active. In the DDCO, we have the lab program 8, where it is said that design a Verilog program for implementing various types of flip-flops such as SR, JK, and D. We have SR flip-flop module, SR flip-flop, and we have inputs and outputs. Input SR, clock and reset. Output B and B bar, that is B dash. Register Q, B, QB, always at post-side CLK begin. If reset, then Q is less than or equal to 0. Else, begin with the case of inputs S, R, 2B00, that is Q less than or equal to Q, 2B01, Q less than or equals to 0, QB10, Q less than or equal to 1, 2B11, Q less than or equal to 1. End case and assign QB not equals to Q. End module. We have the output of SR flip-flop according to the Verilog program. We have given the value of S as 0, R as 0, clock as 0 and reset as 1. As these are input value, you can change them. For the given values, we have the output given here. the next is JK flip-flop. Module JK flip-flop. Inputs and outputs. Input JK clock reset. Output Q and QB. Register Q, QB. Always at H. Pose H. CLK. Begin. If reset Q less than or equals to 0, else begin. Case J, K. Inputs B 2B00. Q less than or equals to Q. 2B01, Q less than or equals to 0, 2B10, Q less than or equals to 1, 2B11, Q less than or not equals to Q. N case and assign Q bar is equals to not Q. N and N model we have taken 2 here because 0, 0, 0, 1, 1, 0, 1, 1 are given twice in the truth table. Same here we have the JK flip-flop. For JK flip-flop, here is the output JK clock and reset. Given values J equals